Okay. And so, yeah, Paul, you want to get started? Kind of introduce yourself and,
Yeah.
like I said, we're very informal, so go as formal as you like.
All right. So my name is Paul Hargis. My information's up here. I work for Workmarks. Scott, Cody, and I, and a few others, run a DFW Data Science meetup. You're welcome to come out there. Some of you already are in that. I recognize a couple of you. So that's good. So anyway, you can contact me later afterwards. Am I a Scala expert? No, I'm not a Scala expert. Am I a Spark expert? No. But I try pretty damn hard to understand what's going on in the universe here. So this is me. Those are the places I used to work. I'm a subject matter expert for, in other words, we have like a 7-state region, South Central. So in that region, I'm the subject matter expert for data science and for Spark, so I'm actually supposed to know this stuff. We're going to go through a couple different sections tonight. We have until, I don't know, 8:30, let's say. So we have about an hour, 15 minutes. So we might kind of do 25 minutes walking you through some introductory stuff, working in slides. But then I'd like to get into a demo later, and there's just all kinds of demos, all kinds of things. So Spark, I also want to talk about Spark 2.0, because basically a lot of the stuff that I'm going to show you tonight is now outdated since they made their release 2 weeks ago. So always pay attention when you're dealing with Spark as to what version you're running, because there will be significant differences between versions. Okay, so why Spark? Okay, Spark is a general purpose computing engine. It's part of the rationale of, same rationale of Hadoop, same paradigm. So Hadoop was invented because processors could no longer scale, single processors could no longer scale to get the job done as data continued to grow and grow. And we had to put data on multiple servers, multiple nodes. And so this cluster computing paradigm came about 10 years ago. So if you don't know, Hadoop is now 10. It's now, they say, entering its teenage years, is what our company says. But I think that's a little premature. Maybe it's in the, what do they call them, tweenies or in-betweens?
The tween.
Yeah, the tween years.
Yeah, the tween.
Not a teenager yet, but it's getting close. Yeah. If you actually go back to the seminal paper by Google in 2004, then yeah, we're getting close. Start putting out curfews and stuff. All right, so why do we need a new data engine? Well, has Moore's Law peaked? Everybody in the room know what Moore's Law is, right? All right. What is Moore's Law? Somebody?
Every 18 months, an approximate doubling in computational power.
Yes. That's right. And so not only hardware companies, but software companies grew to rely on that trajectory. And so they just kept making, software got more complex, hardware would drop in price or stay the same, but you could always count on sort of a doubling of processing power. And at some point, it became apparent that the only way to keep doubling that is to break into multi-core systems. So nowadays, if somebody told you to go out, if your boss told you to go out and buy a single-core CPU, guess what? You're going to be screwed. You can't get them. They don't make them anymore. So they probably do in certain areas like AMD.
No, like verticals?
Yeah, mobile devices, AMDs. Okay, but if you're talking Intel, the typical stuff that you go out and fill your data center with, they're not even quad core anymore. They ran out of names to call them. They're 16 core, 12 core, 10 core. Those are the things. Those are systems. So software has to evolve in order to work under that environment, right? So you can't run the same way when you're running in a distributed. It's not only distributed storage. Now you're distributed compute as well. So that's the formulation why Hadoop came about, and also Spark is that same paradigm. So Hadoop, as I said, has been around 10 years. Spark, who knows how long Spark's been around?
tool? 2009.
2014?
Yeah, so some smart folks over at UC Berkeley in what's called the AMP Lab created Spark, and they wrote the papers around 2010, so, you know, let's call it 5 or 6 years. But it's not really been commercially available except for the last 3 years. So it's a very new technology in you know, if you talk about, compare it to like SQL, how old is SQL? Yeah, SQL's old.
45 years old, yeah.
There's some people in the room who aren't as old as SQL.
Yeah, that's right.
Then there's some of us who are. So, you know, why did they create Spark then? If Hadoop was kind of doing the heavy lifting, why Spark? Well, it's all about, if you sum it into one word, it's about speed, right? So now, basically, you know, kind of a mantra is disk is slow, memory is fast. Now, I will prove that to be slightly inaccurate in a couple more slides. But, so Spark has all of these modules now. So when you do Spark, you're not just running core Spark. You're typically doing something like you're running Spark SQL, or you're doing machine learning, ML Live, you're doing Spark streaming. Anybody working in a streaming environment right now, doing anything with streaming data? Okay, so actually the first demo I have for you is going to talk about streaming, show you some streaming stuff. So then there's graph frames. With the advent of Facebook, graph technologies became necessary. So you can't store all of your friends in, if you're on Facebook, I don't use it, but if you're in Twitter or whatever, all your followers, you can no longer store that in a typical sort of a database that's relational. It just doesn't scale very well. And then the latest on the block is Spark R. Are there any R programmers in here? Okay, good. So yeah, so ours is really kicking into high gear as well. So this just shows, you know, MapReduce uses disk, and it's important to point out that everybody has to read from disk. Nobody walks around with all their data in Flash. You know, you don't carry around these Flash RAMs like, I got the database right here. Now, I've heard recently that, I can't remember, is it EMC that makes Isilon is coming out with a fully 100% SSD storage rack. And so, you know, so SSD, is that disk? Well, yeah, it is. It's just different technology, right? So we get into this tiered storage that we'll talk about. So it's no longer just disk and RAM. We're blurring the lines between storage mediums. So that's why they start talking about tiered storage. Because basically it's all about latency. And yeah, I've got a slide on latency. All right, so Apache Spark, Databricks, this slide's about a year old, so it's not accurate, but it gives you an idea for the popularity. So we said around 2010, AMP Lab in Berkeley, probably what, 3 guys, you know, writing, 3 people, Matei, Zaharia, I think is his name. He's now at Databricks. So, you know, you can tell 2013 it got really popular. So the Apache Software Foundation, by the way, that's really the foundation that governs the open source projects and to a large degree governs the open source world these days. So, you know, it's like the best day in your life when your project gets promoted to a top level Apache project, right? That's when you pull out the champagne. So this has like, these are contributors to Spark. Well, so I was at Databricks just a few months ago, and they announced that they now count over 1,000 contributors. So, and contributor is a very specific term. Okay, so now most of you all in the room write code. Who writes code? Almost everybody writes code in here, right? So a contributor is a bigger bubble. Okay, a contributor can be, I run tests for the project. You know, I do QA. I'm going to help them do documentation. Those are contributors. But committers means submits code to the project. There's over 1,000 committers to Spark. Okay. Now, Spark, back in 2014, set the record for this Daytona Gray Sort benchmark. So Hadoop had been taking the there's various purpose-built SQL engines out there, right? So there's not just one flavor. There's all kinds of things like Vertica, HP Vertica. There's all manner of fast SQL engines on the planet. But Hadoop was playing a heavy role in those. And they ended up comparing a MapReduce job here to Spark. And Spark actually ran 3 times faster. So the TerraSort is doing a trillion records, doing a sort of a trillion records, 100 terabytes on disk, and it won significantly. And it also did it with only 1/10 of the number of machines. So it's not like they just threw hardware at it, right? So it was a phenomenal thing. So everybody writes in more than one language, right? So does anyone in the room only know one computer language? I'm going to call you out right now.
Yeah.
Right. So, I mean, over a course of 10, 20 years, you're going to learn more than one language. You're going to have to sort of survive and thrive, right? So, now some of this is focused with a little bit of slant towards data science, but it's not. That's okay because data science is becoming part of everybody's job. So, these were the languages that were in use to do data science before the advent of Spark. So Python, things like scikit-learn. How many Python developers, who knows Python in the room? Okay, good. I should have you all sit over here. Java people over here, people over there. All right, so now I don't have a comparison for now, but so Spark, you can access Spark in multiple APIs, multiple languages. So we have over here Scala, right? Everybody here, claps for that. Then there's Java, and if you're a Scala developer, you're probably also a Java developer, right? Because you had to come from somewhere. And so then Python, so if you can see that over time now, with the advent of R, well, Python has actually gotten more popular. It's like some was stolen from Scala, and not that this stuff matters a whole heck of a lot, but I was actually curious to find out. So last week we were in Austin?
Yep.
So Jim and I actually just happened to run into each other at the Spark Live event in Austin on the 3rd. And the CEO was talking about a bunch of stuff, but one of the things he said was actually, initially something like 80% of Spark was written in Scala, because a lot of the newer stuff is now tilting towards Java. So I can only imagine that as you get over 1,000 contributors, you've got a heavy preponderance of Java developers, and it's just that's what they know. So I thought that was an interesting thing.
Yeah, the clever thing is that they've got that API working across all 4 languages, and they have it, where you can flip between them. That's ingenious.
Right, and in the demo, I'm going to show you a notebooking tool. There's a bunch of them out there. I actually will show you 2 of them tonight. Databricks as well as Zeppelin and Jupyter. I could show you, but probably not tonight. Okay, so we have to get through some terminology. Anybody in here actually written their own Spark program? Okay.
Well, I'm in the middle of it. It's not done.
That's why you're here, right? That's why I'm here. Okay, so a Spark program consists of several things. Now we'll talk about tasks and jobs and stages later on, okay? But the couple of things I want to describe right away are the driver program and the executor. So now you can run Spark in a bunch of different modes. You can run it in standalone mode, which just says use the machine that I'm running on and take all of its resources and go as fast as you can. So that's standalone, which is a perfectly acceptable way to run Spark. But when the real power from Spark comes from running it in a distributed, in a cluster mode. So in a cluster mode, you have all these nodes out here, and this is just a cluster of these are computers. These are, when I say node, I mean like a server, high power, 16-core server or something. And so what you'll do is typically, you'll have a client out here, which is representing your connection to this cluster. And then you'll have a cluster manager here. We'll call it a cluster manager. So that's true whether it's a notebook, it's true regardless of how you're accessing Spark. And we'll talk later on about the Libby server. We'll talk about some of the new things coming out. Libby server is another way to connect to Spark. Right now, it's like in cluster mode, there's two sub-modes in cluster mode. Okay, so the driver program is typically going to live up here in the client. Okay, so the driver sits right there. And then these executors are down here. And so, these executors are here and here and here and here. And so these things are actually going to start running tasks down here. So a task is a unit of work, right? So you tell, every time you write a program, you're giving instructions. So you're telling it what to run. So the cluster manager then, the job of that, and these things, the two most popular ones are Yarn and Mesos. Okay, so Yarn comes with Hadoop. Any distribution that you can pick is going to come with Yarn. And then Mesos is another alternative. So that's what we're talking about here. So what happens is that basically the cluster manager allocates containers. And these are not Docker containers, but they are containers. And then the executor actually manages the tasks that do the work. So let's get into some pictures before we go much deeper there. So memory model. Spark is about being fast, and it's fast because it uses memory. So guess what? This is the most important thing that you should take home. So get your cameras out, or take a photograph of it in your head, because this is the thing that you absolutely must know. The Spark is built upon something called a resilient distributed data set, an RDD. Now, curiously, in the latest versions of Spark, they steer you away from RDDs. Because, now I'll get to that in a second. But it's, so there's some sort of lineage here. We'll talk about RDDs and then data frames.
Yep.
And so this is a time-based lineage, you might say. It's also an inheritance-based lineage, okay? So, but in the beginning, there was RDDs, right? So what is it? It's a data set. That's where your data lives, right? So that's, if you're wondering where, I just loaded something really huge. Where is it? It's in an RDD. It's distributed because unless you're running the standalone mode, it's not just on one machine. It's distributed across all of these nodes here. So it's distributed. And thirdly, it's resilient. So if it ever becomes paged out of memory or gets clobbered, as long as your Spark context is still alive, it can and will rebuild itself. It is its own responsibility. Its contract with you, if you will, is to know how it was built and to know its entire lineage. So we're going to talk about lineage in a couple different ways. This is inheritance from an object perspective. So Java people are getting excited because we have object inheritance here, right? And I'm a Java developer too. 10 years ago. But, then there was Scott. So squashed everything. So now, the RDDs do two basic things: transformations and actions. Transformations are all those fancy things that you are cleverly thinking about, right? So it's like, oh, I'm supposed to go out and grab that data and massage it and clean it and transform it and all this stuff. So those are all the clever things that people are doing. Maps, map, filter, group by. We're doing aggregates. We're doing sums. So that's where people mostly start. Is like do all these transformations. The other thing, the actions are things like count, collect, take. Those are like, give me some of the data. And that's actually a good thing to remember. So when you run an action, guess what's going to happen? While you're doing transformations, those are happening down here. So you can get a color. So transformations are here and here and here and here. And guess what? When you do an action says, take that data and give it back to me up here. So, first word of caution, don't use collect unless you mean it. Because what collect is going to do, if you load let's say a terabyte of data, if you load a terabyte of data and you go, let me just look at it, let me just call collect and look at it. I'm warning you, you will probably need to reboot. Okay, so Because
Or your email.
what you're saying is, I want all of that data up here on the client. So be careful. So what you typically do is you do a take if you just want to sample the data. Give me a take. Take some of that data. So the other thing is this thing called lazy execution. Transformations are lazily executed. So what that means is they don't actually trigger anything. All they do is they get stored. So when you do a transformation like this, really involves map command that you, let's say you have some CSV data, and so you have a data frame, which is a parent. It's a subclass in RDB. So you do a map, and you have this transformation out here. It's really complicated, and then you're sitting in Spark Shell, and you hit return, and it comes back instantly, and you're like, wow, Paul was right. It is really fast. But actually, what's happened is all that happened is that transformation is stored. It's stored for later execution. So in order to trigger that, then you have to do something like a take or a count or that is the action that will then cause the execution of those lines of code. All right, so a picture is worth 1,000 of my words for sure, but here's what I was trying to draw up here on the board. Okay, so Spark context, that's critical. So if your Spark context dies, your job dies, right? So that's just like, in the Java world we had context as well, right? You launch a web container or something, you've always got some sort of context that you're dealing with. So Spark context, that's sort of like the root of all of these lineages. Now, when we're talking about lineage, we're not talking about inheritance, we're talking about, so basically, I'm going to use data frames even though we're talking about RDBs right now. So we'll say data frame, 1 is then leads to data frame. So basically you do a map and you get another data frame. And then you do a filter command here and you get yet another data frame. So every time we're sort of taking some sort of transformation out there, we're actually creating another data frame, another RDB. Why is that? Why do we have to create one every single time? Because of a certain property of RDBs. Immutability. Immutability, as you know from your Java books, means once you create it, you can't change it. Every RDB and every memory structure in Spark is immutable. So every time you do something to it, you're actually, whether you store the reference to it or not, you're actually creating a brand new RDB. Now this is typically the point at which we get into a 40-minute discussion of memory allocation. We don't have time for that tonight, which I would love to do that with you, but we just don't have time. So here is your first Scala program. If you copy that down, you type that in, and I don't know, Spark 2.0, all bets are off. None of this code can run through Spark 2.0, but that should run. Okay, a note about slots or cores. Okay, if you're running with Databricks, you're going to see that term. They're going to call it slots, and a lot of other things, a lot of other distributions will call it cores. What it means is we can do more than one thing. If you go back to the drawing, an executor can run one or more tasks, typically, at least one or more tasks, and can do more than one thing at a time. So that's basically, it's a multi-threaded model, right? Just like Java, just like C, it's a multi-threaded environment. So, so these tasks can run on multiple cores or slots. Okay, so those two terms are kind of interchangeable, cores or slots. Just be aware of it when you see the word slot. You can think of it as cores, okay? And that might be a better, depends on, I guess, your background, but those are the same thing. So, Spark context is the first thing that gets created in any Spark job, and it's the last thing to be basically done away with. So, Spark context now also is used to create these other objects: SQL context, Hive context, streaming context. So, this is like the root point for Spark SQL. Hive context is a subclass of SQL context, which allows you to fully access the Hive-based query language. Hive, it's just pure SQL now, but HiveQL is what it used to be called. But the Hive query engine is at your disposal. And that's true whether you have a instance of Hive or not. Okay, because when you install Spark for the first time, if you were, and if you're like an inquisitive person, you're like, hey, what? You know, it's got an awful lot of jars. It's like, what are all these Hadoop and Hive jars doing in my Spark build? Well, that's why, because actually, and there's a long history behind this. We can get into Shark and all kinds of other things that would take us forever to talk about. But Shark was like a Spark sequel on Hive. So, you know, and it's sort of a quasi project out there now. Anyway, so context, you got to have context. Remember, before you do anything real in Spark, you've got to have a context to do it. Whether it's, you know, Hive context, SQL context, whatever. So by using also Hive context, you can also take advantage of what are called user-defined functions. So you can create your own functions and give them a name, and then execute those within the query parser. All right, so at some point, somebody in the room was wondering, well, if my data is split across all of these different nodes, I mean, how do I know where it is? How do I know where that piece of data that I want is? Well, so Spark has a way of basically partitioning your data for you. Now, you can actually submit your own partitioner to it. You can create a partitioner class, say, use my partitioner, because I know how I'm going to query this stuff. If you're sort of like the bread and butter of Spark is SQL, right? So that's really what most people's first Spark job has to do, is loading some CSV file, maybe importing some data from a database, and then running some queries against it. That's how you kind of get up and running with Spark. So you can define how your data is partitioned. But then again, you don't have to. You can just leave it up to, you know, Spark. Do the right thing. Data locality just means data locality is running computations on the data where it lives. That's the same paradigm that Hadoop uses. I'm going to skip over some of these things. Closures. You guys probably, mostly I skip over this, but since you're Scala, I'll ask you now. So a closure is basically an immutable chunk of code and data. So we're used to having immutability in terms of data. Like if we say a piece of data is immutable, you know, then it can't be changed. If it's mutable, then we can change it. And code is sort of like, this is where the functional programming paradigm came in. It's like, well, for ages we've been just running code and not caring whether that code was immutable, you know, whether it was changeable or not. Well, guess what? It turns out that in a complex world that we're running in these days, these cluster environments, these distributed computing environments, mutability, or rather immutability, is one of your best friends. And so that's because code that can be changed or modified or broken, you know, in runtime is not very good code. It's not code that you ever want to debug. Right? So, you know, we've all spent time in the debugger. Can you imagine trying to debug a cluster worth of data and not knowing where your code's running, which node it happens to be on? If you run it again tomorrow, it's going to be on a different node, right? And so, you know, where are the log files, and how do I figure this out? Can I stop it and debug it? It's a nightmare. So that's one of the main drivers upon that functional programming came out of. It's like the code ought to not be, it ought to be immutable. It ought to be sealed. So what happens is these closures are created, and the driver sends down a closure which becomes a task to the node. So I've mentioned tiered storage. And so all these different tiers here. You can see there's at the top memory only. That's where we want everything to run, right? So, you know, if your data won't fit in memory, what do? You go buy more memory, right? So, if you can't go buy memory, which is really what you should do, then you're stuck with one of these other things. So, you know, way down here we have disk only, we have memory and disk, and then we have serialization. Now, this is before tungsten, so remember that word tungsten. Tungsten is the new way. This is the kind of older way that still is around if you want to use it. But even early on in the Spark journey, it became apparent that, guess what, not every data set fits in memory, as much as we would like it to. So does your job just crash? Well, luckily the answer is no, it doesn't just crash, but it gets slower. And so stuff will start to page out to disk, memory and disk, and it may or may not be serialized. When it does so, that's Java people, we all know about serialization and deserialization, right? You know, it's like, it's always on your mind. And and if I scroll down here, over here, there's this other thing called off-heap. So Spark started to take advantage of off-heap memory, and that means that the garbage collector cannot get to it. You know, basically, it's not part of garbage collector's cycle, which is a really important distinction. Now, I told you we would talk about latency, and this ties back into tiered storage. So remember the first, like slide 3 was, you know, disk is bad, memory's good. Remember that slide? Disk is bad. Okay, so there's not just two things. We're not just dealing with disk and RAM anymore, because in the latest efforts around Spark 2.0 are like, they do something called, they do runtime code generation in Spark 2.0. And so they're generating code on the fly at runtime, which, you know, that like gets me all wondering about the functional programming paradigm. But anyway, they do it. And so it's like, well, we're trying to, you know, we want to run fast, so we want to stay in RAM. Well, turns out all RAM is not created equal. So you guys know about level 2 and level 1 cache, right? So, so you know that once you get something really tightly cached in level 1 or level 2 cache, it's going to run even faster. And in fact, if you compare these numbers, so here we are at 150 milliseconds, let's say disk seek 10 milliseconds, okay. Some people, you know, when you start out programming, 10 milliseconds sounds fast, right? Well, that's really fast. But it turns out to be really slow. And so by the time you get to L1 cache, now you're talking 3 microseconds. Main memory, 100 nanoseconds. Now we're to the nanosecond region. But guess what? To make things run at an acceptable speed nowadays, people are looking for ways to completely get off of this map. And what's faster than L1 cache? Anyone?
Registers?
CPU registers, right. So they're looking for ways in that code generation that we just talked about, like, hey, I don't even want to get outside of a CPU register. That slows me down. So that's where they're going with that. All right, so we're going to have about 2 more sections of these slides. I'm going to go into core, and then we'll take a 5-minute break, and we'll come back and do a demo around 8 o'clock or so. So we've got about 15 minutes to get through some more stuff. Okay, so RDDs. So if I already told you that RDDs are like prehistoric and don't, you know, they're gone, it's not really true. RDDs are there, they still exist, you can still get to them, and you can still create them and run with them. However, you do so at a cost. You do so at an injustice to whoever's paying your salary. So basically, so here's all, and I'll tell you why in just a second. So these are all the various types of RDDs. Map partitions, pair RDDs, and it's language specific. Some of these, like there's a Java pair RDD or paired Java RDD or something like that. Of course, you can always go back to the Java doc, the Scala doc, whatever, which, you know, it's like if you remember when we were writing Java code, we always have that one browser page that has the Java docs open, right? You always have it right there. Well, now you'll have that Scala doc open always in one page. But so you can find these things and find out, you know, about them, what they do. So here we are, transformations over here and actions over there. These are the things that actually trigger execution. These are things which, clever though they may be, actually just get stored until an action is called. Now, I'm going to talk about data frames and a little bit about data sets. So, if you're using, data frames came out, I think, in Spark 1.4, which was way back, like, I don't know, 9 months ago. The Spark, by the way, is like most products that you deal with, that you're, like if you're dealing with Microsoft, which I love, they're a partner of ours, or Oracle, or somebody like that, how often do they release a major release of their product? It's no more than once a year. It's probably less frequent than that. Well, in 2015, Spark had 4 major releases, and then a 5th one, January 4th, 2016. So basically 5 releases in the span of a year. Major upgrades to each one of them. That's why I caution you, always know your Spark version, what you're dealing with, or you're going to get confused. Also, you want to go to the proper Scholar or Java doc for the right version as well, because you can also get misled. So data frames came about for a couple of reasons. So those of us, first of all, who are Python developers, what is our version of data frames? The library called
No, pandas.
Pandas.
Oh,
Yeah. So Python is really kind of formative in the machine learning area because so many people were using Python to do machine learning. So they wanted an abstraction just like Pandas data frames. So they built this data frames module to be sort of a high-level API, almost a DSL, if you will. It has this domain-specific language. Instead of writing a long, I mean, I love SQL as much as the next person, but at some point it's like, I'm like, try to do really complicated things in SQL, and you start to scratch your head and wonder, why am I doing this? So the data frames came with an API where now you can just say, instead of writing the SQL, you can say .filter and put your filter condition right there. And it's the same as .where for the SQLholics. So we can write where if we want, or we can write filter. It's identical. It's an alias. Same thing. So that's one rationale for data frames, but it's even way more important than that. Next thing is that, remember we talked about, and by the way, so this low-level API still exists. This high-level API is what you should use, and here's why. Tungsten. So I showed you that chart of tiered memory and tiered storage. Tungsten is a newer binary formatted data type, and it has a couple of key things. So remember we talked about serialization. Well, what's the first thing that you think when you hear the word serialization? You think, it's going to be slow, right? And now I've got to serialize this stuff. On the other end, I'm going to have to deserialize it, rebuild those objects. What a pain! This is going to be slow. It turns out, yes, it is slow. So what they did was they built this binary format, and they built it around encoders and decoders. So now the format in memory is the same format on disk. It doesn't have to be serialized in between. Store it in Tungsten, and then shelf it in Tungsten, and you're good to go. You lift it off, and you're ready to go. So it's basically built around decoders, encoders and decoders. So there's encode and decode, and it's a binary format, which is much faster. It's stored in a lot less space, so you consume a lot less RAM. That's good. So lower memory pressure, and it's faster because you don't have to go through. It's not like either in object or in wire format. It's like does both.
So they use DMA?
Was it
So take advantage of DMA?
direct memory access?
Yeah.
So probably
DMA transfer.
in terms of transfers from memory up into bulk memory store.
Either direction.
Okay, great. Yeah, that's my understanding. And so it's basically you no longer have to. You used to be able to pick your serialization method. There was Cairo and there was Java, and everybody said Java was slow. Java serialization, don't use it, it's too slow. So they came out with Cairo. And then they came out with Tachyon as a memory, kind of a way to preserve your shuffle data and long term. So that's what Tachyon. But then Tachyon got renamed to Alexio, so now it's Alexio. It's like when we get presentations from Hortonworks, it's like the animals in the zoo, right? We've got stuff called banana and cabana and all kinds of stuff. So there's lots of animals in the zoo, but all right. So I told you could use RDDs, but then I said don't do it. Well, these are the reasons that you might want to do it. You want low-level transformation, and maybe, just maybe, the thing you want to do is not get available at the high-level data frame API. That's possible. Now, the longer you wait, more stuff will be there. But if you're running in 1.5, there's a good chance you're going to dip down into the RDD level to do some things if you're running in an old version like Spark 1.5 or 1.4. There's a few other things in here if you want to impose your own schema, etc. And there was even something here called, in between here, there was something called a schema RDD. You may run into this term, schema RDD. This was like 1.3. So this was basically the predecessor of the data frame, schema RDD. And now I don't even think you can get to this. RDDs are still around, but I'm not sure that this is even there anymore. Only if you're using 1.3 or something like that. So that was the initial schema. But what it is, the way to think of data frames is it's a schematized object. Okay, so it's not just your data, it has schema rolled into it. So data frames are basically you use data frames for everything else, is one way to look at it. But now we get into the data sets. Okay, so I mean, it's like hard to keep track. First you told me RDDs were the thing to use, then there's the schema RDD, then there's data frames, and now there's data sets. Why can't we just stick to one thing? Well, so data frames, just like their pandas equivalents, are not typed. And so so they created data sets to give you that strong typing, and give that back to you. All right, so and the way that a lot of Scala development now is using case classes. So you use case classes, and that's like your, what do they call it in the Java world, your bean classes, Java beans, when you read in a set of data, and then you say, hey, I want to create an object called, product ID. I want a product. So you build basically you get a Java bean class, and you call it my product or product class, and then all of those attributes get loaded into that product class. Well, that's basically what you're starting. You can do that in Scala as well through a case class. So you see some code that does that. But data frames is where you're going to spend most of your time. If you don't need type safety, then data frames are for you. All right, so also we're going to talk about catalyst optimization and the benefits of tungsten. So if you want a higher degree of type safety at compile time, so that's the difference, right? So, I mean, all data has a sort of a type, right? Or, even in Python, okay, it's duck typing. It's like an object can be interpreted one way one time and slightly differently the next time. It's duck, just try to work with it as best you can. So anyway, data sets allow you that type safety at compile time, and but you can still take advantage of Catalyst and benefit of Tungsten's efficient code generation. All right, so we'll get into that in a little bit. Now, we're not going to get into these things in detail, but so data frame, there it is. That's data frame. Sorry. Runtime type safety, static typing. Performance and optimization, that's the really key one. So as I was drawing on the board over there, basically this is what's happening. So say you run a job and you're doing a read from SQL or CSV. So there's that disk up there, and now all of your data is populated through all of these different nodes. And so you have all this data strewn about. Then you perform various transformations on it. So we create new RDDs coming down. And then we do a count. That causes data to move down here. So this is what would be called a logical model of that transformation. So I'm showing you this so that I can get to the next piece, which is Catalyst Optimizer. So that's where we're headed. Okay, so now, it looks like not a very big deal until you start to think about, well, could be multiple millions of records in each of these locations. And so that's why we don't do the collect as our first experience with Scala, right? So what we do, or with Spark. So what we do is, we can do a count because that's a very low cost thing to do. Now it has to it has to run, so they basically take local counts at all of the various nodes and then forward those, and that's the MapReduce paradigm, right? So if you go back to MapReduce, that's what's happening. It's the same paradigm. Run a transformation up here where the data lives, forward the results down, and then combine them or reduce them to a single answer. That's what you're doing. Now, I showed you all of this so I could talk about this. So, Catalyst Optimizer came about in, I don't know, Spark 1.4, maybe 1.5. 1.6, it got improved significantly. In 2.0, it's again improved quite a bit. So this is SQL AST. I forget what AST. It's
Abstract syntax trees.
okay. Yes. No, thank you. So basically, your SQL code and your data frame code are both going to feed into this optimizer. And so this is like the pipeline for the optimizer. And so what happens is every time you run SQL or you do an operation or a transformation on a data frame, it's going to go down this route, okay, this Catalyst Optimizer. So you basically have a logical plan, and then if you have to reference the catalog, that could be the Hive Metastore, for instance. It's like, okay, there's schema involved here, so let's go get it. And then we produce an actual logical plan. So if you spend all day at your SQL engine, you know exactly what this is, right? If you're a master of SQL, then you know exactly what this is trying to do here. So then you come up with an optimized logical plan that generates multiple physical plans, and then you have a cost-based optimizer, right? So that cost-based optimizer says, what's the cost of doing plan A versus plan B versus plan C? Well, C looks like it's going to be faster, let's use that one. So that's what's going on each and every time. So in the like 1.5, 1.6, you would get optimization, and in 2.0, you're actually going to get code generation at that point. Catalyst is going to allow you to generate efficient code at the far end of that pipe, right there, which then will store the results back in the RDD. So these are the stages: analysis, analyzing a logical plan to resolve the references, logical optimization, physical planning, and then at the very end of the pipe, code generation that ends up in bytecode. Just a glance at data set, because we're not going to talk about them again. But like I said, that case class person, so you have name and age of person, that's your Java Bean class, right?
You just hit it.
Okay.
You told me to tell you.
Yes, you're right. Good. We're almost there. We'll take a break in about 3 minutes. 5-minute break, and I'll fire up a demo. Okay, so this is kind of the code that you would use to create that. So you have a data frame that you read. You have a people.json. By the way, Spark is really good at reading certain types of data like JSON because you can infer schema. You don't have to, it's like, God forbid it's XML or something like that where you have, of course, if you're a bank, you love XML schema, XSLT and SOAP messages and all of that stuff, right? And you've got to deal with all that stuff because, at some point somebody's going to get blamed if something goes wrong, and they got to find out who. But JSON is more free flow than that, right? So we don't have JSON schema typically, but Spark can read it and infer the schema from it. So, and that includes multi-layer JSON. So that's really good. I know people who are using it just for that reason. Let Spark read it in, infer the schema, pass the schema upstream, and we'll deal with it later. So, but anyway, it's as easy as saying, dataframe.as and then a case class instance. And so that will populate or create an object of basically typed as person. So this is where data sets came from. This is why they exist. All right, so I keep coming back to performance because Spark is about performance, right? So we talked about RDDs, and if you notice, the red stuff is RDDs. Guess what? It runs a lot slower. So time to aggregate 10 million int pairs. These are the times. Now this is 1.6. So 2.0 is another big. You'll see some other charts for 2.0 that will basically clobber these numbers right there, the green. But basically, and if you go way back in time, so again, if you're using an old version of Spark Python, the Python API, they used to implement a lot of the functions in Python. So you kind of had two separate Sparks. You had the Python PySpark, and then you had Scala Spark. And So the Python stuff was much slower in runtime, right? Because Python is, primarily an interpreted language. And so it's just slower than a compiled bytecode form of it, like Scala. Well, so what they did was they changed that around 1.5, I think, around 1.5. Python just became a thin wrapper, just enough to interpret what's going on and then make the call to the Scala libraries. So it thinned down in terms of its real estate. It got a lot thinner and faster. Guess what? So basically there was very little difference between Scala and Python at that point. You can see there's virtually no difference. But the main thing here, I think, is the main difference here is tungsten. Tungsten is the main difference in that. Here's just a quick type universe. Data sets give you the best of both worlds. RDDs are type safe. Data frames are not. Data frames are useful for all the things listed there. Data frames are where you spend most of your time right now if you're working in Spark. Now I'm going to skip over this section, and we can come back to some of the yarn stuff if we have time. But let's take a short break, and then I'll fire up a demo.